Okay, so in this presentation, we will observe the moves, paths, and walks of different chess pieces in an empty chessboard of varying dimensions. Our main objective is to focus on the chessboard and the different chess pieces, the manner in which it moves as the number of moves varies. We will also cover different dimensions of the chessboard of higher, say, 2 or 3 dimensional k dimensional boards for the rook specifically. Let us observe the chessboard. The chessboard of 8 cross 8 has 10 different distinct squares. We have colored it with 10 different colors. We have U1, U2, U3, U4, U5 till U10. Now this is based on the symmetry of a square. A square has 3 lines of symmetry, 4 lines of symmetry, 2 across the diagonals and 2 cutting the both sides. So it makes 10 distinct squares in the chessboard. Now this will be important later on. Now let us observe the chess pieces. A king moves one step forward, backward, sideways, and in both diagonals with a distance of 1. A queen has the same as a king, but the distance is much higher up till the size of the board. A queen can move in 21 directions, 21 different squares from the corner, and up to 27 from the center. A bishop moves in the diagonals. The rook moves forward, backward, horizontal, vertical. And the knight moves in the L shape. Now, let us observe in detail the squares. We find that the distinct squares for an L cross L board will be let's say the dimension of the board is 2m cross 2m. Then one half will be m, the other half will be m, and we have m minus 1 up till 1, which is m into m minus 1 by 2, the total number of squares. For 2m minus 1 cross 2m minus 1, we have m minus 1 till 1, which is again m into m minus 1 by 2. So when m is floor of L plus 1 by 2, this m will just be this m plus 1. So we have m into m plus 1 by 2. In this case. Anyway, so this will be useful for calculating the moves for a king, a queen, a bishop, and a knight. Keep this in mind. Now, let us find the number of ways for a queen in a 4x4 board. First, for a warm up, let's look at a 3x3 board. A queen moves in 6 different ways from the corner, and it moves in 8 different ways from the center. In the edge, also it moves in 6 different ways. So we have 3 distinct squares. Similarly, in a 4x4, also we have 3 distinct squares: the corners, the edges, and the center. All 4 centers are similar. They have a symmetry, rotational, and otherwise. So is the corners, and both the edges are symmetric about this line. So we have 3 different squares colored red, green, and blue, red, green, and yellow respectively. So we let's assume Q1 of n as the number of ways a queen can move from the corners, and Q2 as the edges, and Q3 as the center. We observe that Q1 has 9 different ways to move: 3 on this side, 3 on this side, and 3 on this side. Similarly, for Q2 as well, 9 different moves. Q3 it has 11. 3 from the center, 2 on the corners, and remaining 6 on the edges. The following describes the moves of the queen. Now, let us take an example. Q1 of 1 is equal to Q2 of 1 equal to 9, which is Q3 of 1 minus 2. Now let us look at Q1 of 2. Q1 of 2 is simply we add three other corners, that is 3Q1 of 1 plus 4Q2 of 1 plus 2Q3 of 1, which is nothing but 3 into 9 plus 4 into 9 plus 2 into 11. Let's look at Q2 of 2, which is nothing but 9 from here, 9 from here, 9 from here, 11, 11, 11, 9, 9, 9. So we have Q2 as simply 6 into 9 plus 3 into 11. Note that 6 plus 3 is 9. And here we have 9, 9, 9, 9, 9, 9, 9, 9, 11, 11, 11. So we have 8 into 9 plus 3 into 11. So Q3 comes out as the largest and Q1 as the least. Now, one can form certain one can form certain recursive relations. It is said as the following: 3 red, 4 green, 2 yellow, 3q1, 4q2, 2q3. After making one move, it must move in either of these squares. Therefore, after making the first move, it must make remaining n-1 moves from these squares. Therefore, we get the following three recursive equations. Now, we can simply take q1, q2, q3 as a matrix. Then we get the following relation: 3, 4, 2, 2, 4, 3, 2, 6, 3, q1, n-1, q2, n-1, and q3, n-1. We get the following matrix relation, which is nothing but now this is because q1, q2, q3 of 0 is 1. Now this is assumed as default because q1 of 1 is nothing but 3 plus 3 times q1 of 0 plus 4 times q2 of 0 plus 2 times q3 of 0, which must be equal to 9. Therefore, all of them are 1. Now, one can solve this matrix. Assume this matrix as m suffix q. Then q of n is nothing but m suffix q times 1, 1, 1. Now one can m suffix q of n. Yes. Now using matrix calculators, one can find out that the eigenvalues of this matrix, the largest eigenvalue is 5.85. Sorry, this is a different matrix. Um, we get the following as the eigenvalues of A. The largest eigenvalue is 9.577. the largest eigenvalue we get is 9.5778. And one can state that Q of 100 is approximately equal to the spectral radius of Q spectral radius is the largest eigenvalue one can make this generalization times the spectral radius of the now.